Now, I'm not really looking at a finite collection of points. I want you to consider the region under the graph of this equation, over there from A to B. Now, if that's made out of a piece of metal, I refer to that object as a lamina. I guess I should spell it, shouldn't I? And to find that center of mass, or shall I sometimes refer to that as a centroid, then for that big piece of metal, I'm going to have to make some assumptions. Got to make sure it's very, very thin, and I'm not going to talk about the thickness of this sheet of metal. The second extremely important criteria here is that this piece of metal has to have uniform density. If it doesn't, then the density is going to depend on where the point is, which means it's going to be a function of more than one variable. I cannot discuss that until next semester. So when we discuss multivariable calculus, that's typically third semester calculus, we'll allow the density to be non-constant, identify how we can compute the center of mass or the centroid of a lamina. So for now, if I did partition this into n subintervals, over that I subinterval, we'll choose an arbitrary value of x, call it x by asterisk to go straight up to the curve to determine the height of the approximating rectangle. And as long as delta x is very, very small, I think this gives me good approximation of the centroid of that one particular piece of this lamina over the I subinterval. Notice I'm only going halfway up to the y coordinate. There's where the factor of 1/2 comes in. Now, I do think the moment with respect to the x-axis is going to be yet again another sum. Now, do you mind if I don't write the summation notation? Because you know what's going to happen. I'm going to take the limit of the Riemann sum, which will turn into a definite interval. So do you mind if I just write these sums as definite intervals? So the moment with respect to the x-axis is going to be the sum from one x value to another. Now, in the integrand's position, I'm going to have mass times distance. Now, at any given point, its distance from the x-axis is simply going to be 1/2 f of x. Now, taking a peek at the mass, isn't the mass considered just nothing more than density times area? I know it really should be volume, but I remember I was considering a lamina with a really, really thin sheet. So we'll think of the mass as nothing more than density times area of the rectangle. Well, the density may be unknown, call it rho. The area of the rectangle is just length times width. Wouldn't that just be delta x times f of x by asterisk, which turns into an f of x dx. Now, I think likewise the moment with respect to the y-axis is going to be some interval. Now, yet again, let's talk about the distance I am from the y-axis. My distance from this point to the y-axis is just the x-coordinate. Mass isn't going to change. It's still density times the area, which is this. Now, the total mass can be interpreted as the limit of a Riemann sum. But that's just going to be the sum of the product of the masses of the individual particles, which are nothing more than rho times f of x dx. That is to say, density times the area of those rectangles. So, in computing x bar and y bar, oh, everybody, I think I goofed. I don't think I have enough room. Let me say that one more time. To generate x bar and y bar, I will think of them as these ratios. Or how about better yet saying this? Now, the moment respect to the y-axis is really this expression right here. And so if I pull out that constant rho, here's what I get. Here's my total mass. Oh, but I forgot my rho. I'll pull it out. Likewise, down here, my mass, or excuse me, my moment with respect to the x-axis is really 1/2 of this. I'll pull the rho out. And again, here's my total mass. But everybody, two things. Number one, notice how these constants rho cancel each other out upstairs and downstairs. Number two, take a peek at this definite interval right here. And this interval right here. Is it not true that what they're both being divided by is a definite integral that literally can be interpreted as the area underneath the graph of the equation y equals f of x, as x ranges from a to b? So let me call it what it is. Area. Don't take this the wrong way. I'm not suggesting that this is easy computated. You have to compute it by evaluating definite integral. But in the end, this integral here, as well as this one here, simply represents the area underneath my curve. So here are two useful formulas to come up with a centroid of a lambda